Hello everyone. Today we will be looking at linearly independent sets and bases. So before we talk about the linear independence and basis sets of vector spaces, we're going to do a little recap. The first thing we are going to be looking at is a vector space. Now remember, a vector space is a non-empty set which is equipped with two operations. Those are the addition and scalar multiplication that satisfy the 10 axioms. Now, the next part, which is more important, is also the subspace. So we say a subset of a vector space V is a subspace if the zero vector belongs to H. If I take two elements from H, their addition also belongs to H, which basically means it is the subset H is closed under addition. And if I take a scalar multiple of an element of H, and once again it belongs to H, then also that H is closed under scalar multiplication. So all these four properties make H a subspace of a vector space V. Now, very important part, if you take a spanning set of vectors from a vector space V, this spanning set is always a subspace of the vector space. Now, there are two trivial subspaces of every vector space. That is the zero subspace and the vector space itself. So remember, this is the zero subspace. Now, then we talked about a null space of a matrix of a size n by n. A null space is always a subspace of Rn. What is a null space made up of? It is all the vectors which are mapped to the zero vector. In other words, the null space of A is a collection of all those vectors x in Rn such that when A acts on x, it goes to the zero vector. Then the column space of a matrix is a subspace of Rm. Now remember, we are taking a very general matrix of size m by n. What's a column space? It is a collection of all linear combinations of the column space or columns of the matrix A. So column space of A is a collection of all those vectors B such that Ax equal to B. And this X is in Rn. So it is basically all possible linear combinations of the matrix, of the columns of the matrix A. And as it is a collection of all those B such that Ax always equals to B, which simply means that this matrix equation is consistent. Now we're going to look at the two vector spaces and a linear transformation from one vector space to another vector space. So let's T be a transformation. So I'm looking at T, a linear transformation from one vector space V to another vector space. As it's a linear transformation, so it means that if I take two elements of V, when T acts upon it, then it equals Tu and Tv. Also, so it is basically preserving the addition. And then alpha times U is equals to alpha times Tu. So it preserves the scalar multiplication. Now, so very important part is the kernel of T and the range of T. So the kernel of T is the collection of all those vectors in V such that when T acts on V, it goes to the zero vector in V. So we can think of this as a linear transformation. I have two vector spaces. So kernel of T is the collection of all those elements in this little square, almost a square, and it goes to the zero vector in the vector space W. This is not one circle, it is a zero vector. So let me make that, so this is it's going to one element. Remember that. It's going to one little element. This element is the 0 vector. Okay? Now, then we have the range of T. The range of T is a subspace of W, which simply means, suppose I have two vector spaces, V and W. So I have some elements, say in this little triangle. This is the range of T, where every element of V goes to this one. So this is called the range of T. Now remember, W is called the codomain. That means there are some elements in W which do not have elements here in V. Okay, so the range of T means all those elements in W, so this little triangle here, which have an element in V, the vector space, and they're related by this relationship du equals W. Now, if this linear transformation happens to arise as a matrix transformation, then the kernel of T is nothing but the null space of the matrix A, and the range of T is the column space of the matrix A. Now, this A, guys, remember here, is the standard matrix corresponding to the linear transformation T. Okay, now let's start with our section on linear independent sets and bases. Now, so here what we are going to do is we are going to extend the notion of the spanning and the linear independence from a Euclidean space to vector spaces, and also we're going to introduce the concept of bases in a vector space. So first of all, what is the meaning of a linearly independent set in a vector space? So if I have a set of vectors, these vectors are coming from the vector space V, and I put them in a set K. Then I say K is linearly independent if this equation C1V1 plus C2V2 plus dot 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 CP VP equals 0. Now, if this equation has only the trivial solution, that means the only way this equation will hold if each of the CI's are 0. And these CI's are the scalars or the coefficients or the constants, whatever you want to call them. Okay, so the linear independent set in a vector space, remember, is the set which satisfies this equation 1 with the condition that each of the CI's is only going to be 0. So what's the flip side of this linearly independent? That means if it's not linearly independent, it's going to be dependent. Okay, so let's look at the linearly dependent set. It says the same set is linearly dependent in a vector space. Now, when I say the word in a vector space, it basically means the vectors which are being in the set K are being taken from the vector space V. So this set is linearly dependent if this equation 1, the one here, has a non-trivial solution. What does that mean? If this is going to have a non-trivial solution, that means there will exist at least one CI such that which is non-zero. So we say a set of vectors is linearly dependent if there exist scalars, not all 0, such that this equation 1 holds. So if you recollect back to chapter 1, it's basically going back to chapter 1, guys. The only thing I've added is these vectors are coming from a vector space. That's it, nothing new here. So let me give you a recollection of things we have looked at. Okay, notice this one, guys, is your vector equation. Not only it's a vector equation, it is a homogeneous equation. I just want you to make sure that whatever we are doing, guys, it always has connections back to things we started in the very beginning of the semester. So it's a homogeneous equation, it's a vector equation, and also this homogeneous equation, for it to be linearly independent, Remember section 1.7? What does it tell us? That these vectors are linearly independent if and only if this homogeneous equation has a trivial solution. Okay? And if it does not have a trivial solution, what does it become? It becomes linearly dependent. And that's what it is. It's simply going back to our little chapter 1 always. Okay, now we need to do some examples. The only thing remember now is these examples, guys, will be coming from your vector spaces. In other words, the elements or the vectors which we will be applying are coming from a vector space. So let me look at this L. Okay, so let me look at the set. So if you notice, each of this element is an element coming from M22. So what I say, okay, let me know whether these 4 elements which are coming from the vector space M22, are they linearly independent? So I say, okay, let this be L. The set is L. So what I do is make my life simple. I don't want to keep on writing every time these elements because there are quite a handful of them. So I'm going to say, hey, let the first element be A1, A2, the second, third, A3, and A4. Now, if I want to prove that I want to determine if it is linearly independent in the vector space M22. If you've forgotten, remember M22 is a vector space which consists of all possible matrices of size 2 by 2. That's what is this. And we have proved that this is a vector space. Now, to prove that this is linearly independent, that is the question. It's not said to prove. I want to know whether it is linearly independent. So what is the definition of linearly independence? Say, let C1, C2, C3, and C4 be scalars. Now, if this scalars and if the set L is linearly independent, that means if I take this equation C1 A1 plus C2 A2 plus C3 A3 plus C4 A4 and equate that to 0, the only way this equation will hold if all the CIs are 0. That's what we have to prove. If I do this little matrix, properties and additions and scalar multiplications, will I be able to ultimately get the CIs to be 0? Let's go ahead and plug in. So C1 and A1, we got this matrix, C1, A2, C3, A3. So I'm just now in place of A1, A2, A3, I'm just plugging in the matrices. Then here is a scalar multiple of the first, the second, third, and fourth. And then we simply add these matrices. We can do all of that because each one of them have the same size. So what happens? We get C1, 2C2, minus 3C3, and 4C4 equals 0, 0, 0. Now, by equality of matrices, this can be only possible if C1 is C2, C3, C4 is 0. So clearly, we started with this equation, and we found that the only way this equation will hold is that when all the CIs are 0. And that is basically the definition of a linear independence. So then we say, yes, L is a linearly independent subset of M22. Remember, it's a subset because M22 is an infinite set of all possible matrices of size 2 by 2. And this L only has 4 of them. Okay. Now, let's look at the scenario. If I have a set of infinite many vectors, then the question comes up is that set of infinite vectors coming from a vector space linearly independent? And the answer is it is going to be linearly independent if every finite subset of that set is linearly independent. Okay, let's look at an example. So I'm going to take now example from elements from P3. Now, if you remember, it is the set of all polynomials of degree at most 3. Now, we all know that this P3 is a vector space. So now we want to prove or want to know, it's not proving, we want to know if this set S is linearly independent subset of the vector space B sub 3. Once again, you just go back and apply the definition. You say C1 times x cubed minus 2x plus 4, that's one of the elements of the set, plus C2 times x3 plus 2x squared minus 2, plus C3 times 2x cubed plus x squared minus 3x plus 5 equals 0. So that's what we always have to start with. So if my set S is linearly independent, then this equation 2 will have C1 equal to C2 equal to C3 to be 0. Okay, now let's go and just start with the calculations. So equation 2, now what I'm going to do is I'm going to rewrite this equation, and here I'm going to write it as a polynomial with the highest degree 3 because that's B3. So I'm going to get all the elements which are connected to x3, x2, x and the constants. So we get this one. Now this one, when we do, we can by the equality of polynomials, this element, which is the coefficient of x3, is equal to 0. The coefficient of x2 is equal to 0. The coefficient of x is equal to 0. The constant terms are 0. What do we end up with? We end up with a linear system of equations of variables C1, C2, C3. Now, we all know how to solve these problems. Where do we go? We go back to section 1-2, which is basically applying the row echelon form. And then what we do is when we find that, I hope you're a pro in that by now, this one will have infinitely many solutions. So as it's going to have infinitely many solutions, that means I will have non-zero vectors. And one of the solutions is actually this, where C1 is 3, C2 is 1, and C3 is minus 2. So clearly, S is not linearly independent. Rather, S is a linearly dependent subset of P3. Okay, one more example, guys. Okay, remember we also talked about functions. A set of all functions, continuous functions. We have talked about that in section 4.1. I gave you some different kinds of vector spaces. So I'm taking the example from there. So if I have a set of vectors, 1 cosine x, cosine 2x, and sine square x, and these are, we would like to know whether this set of vectors is linearly independent in the space of all continuous functions on the interval 0 to 1. Okay, you'll have to remember your trig, guys, here. Now, going back to your trig, double angle properties, sine square x is 1 minus cosine 2x by 2. I can write this as half minus cosine 2x by 2. So this term, one of the terms in the set sine square x, can be written as a linear combination of the first term and the third term. Half times 1 minus half times cosine 2x. So clearly, what we see is, so if I write it in a different form, I have half times 1 minus half times cosine 2x minus 1 times sine square x. I'm just, taking this equals 0. So what do we see? I see an equation where I have constant terms, not 0. And hence, it's linearly dependent. So that's going back to things we have learned earlier. So what basically takes back to the things we have learned earlier is that the set of non-zero vectors is linearly dependent. I'm saying non-zero because if it's a zero vector, it's automatically linearly dependent. So the set of non-zero vectors is linearly dependent if and only if, even if one vector, like here sine square x, can be written as a linear combination of the others. Now remember, a linear combination of even one vector, that makes it linearly dependent. Okay, so now I would like you guys to do the following problems from the book. Now these are questions 1 to 8 in section 4.3. I would like you to just find out which of the sets are linearly independent. Thank you.